Okay, in this video, we're going to move on from exponential functions and talk about another type of functions called logarithmic functions. And logarithmic functions are closely related to exponential functions, and we'll see why in just a little bit. It's based off of how we define logarithmic functions. So let's start out, though, by just looking at what a logarithmic function looks like. So with a logarithmic function, we use the shorthand of just log notation, and then you'll have some number. I'm going to use the variable b for base. You'll have some number as the base of the logarithm. And then you'll have an input, and of course it'll be equal to some output. But how we define a logarithm is a logarithm asks the question, what power would I need to raise b to in order to get x? Another way I can write this, of course, is just mathematically by saying b to the y gives me x, right? The output represents is that answer to that question, and so b to the y will give me x. So that's how logarithmic functions are related to exponential functions. So a couple of things to keep in mind with logarithmic functions is just like exponential functions, this base that we use for the logarithm, we're going to go and assume that it's strictly positive, that it can't be 0, and it also can't be 1. But if we were to graph a logarithmic function, it would look something like this. And of course, it'll vary slightly depending on what the base of the logarithm is, but it'll always have the same general shape. So one thing you might notice about this is if you look at the domain, right, your possible x values, I'm limited to just positive values. With logarithmic functions, you can only plug in positive values for your inputs. The logarithm of a negative number is undefined. But the range can be any value from negative infinity to positive infinity. Okay, so now that we know that, we come to the question of what makes logarithmic functions special? Why do we need them? Well, the reason why is logarithms actually have some really cool properties. So let's look at some of these. First, what happens if you take a logarithm, base b, of the number b? So log base b of b. What will that give me? Well, remember, this is asking the question of, hey, what exponent do I need to raise b to in order to get b? Well, if I want to keep it the same, I can raise it to the exponent of 1, because b to the first is equal to b. Well, similarly, what would happen if I take a logarithm of base b and evaluate it at 1? What's log base b of 1? Well, this is asking what exponent would I need to raise b to in order to get 1? Well, this is a property of exponents that any number raised to the 0 power will give me 1. So this is true because b to the 0 power is equal to 1. So log base b of 1, log of any base evaluated at 1 is going to equal 0. Moving on, this is where the properties get really cool. If you have log of base b of two numbers that are being multiplied together, I'm going to use capital A and B because we're already using lowercase b, then I can actually split this up into two different logarithms that are added together. Notice, though, that the base of the logarithm stays the same. The base is still lowercase b. And you might be wondering why this works. Well, it's all based off of exponential properties because these two things are very closely related, logarithms and exponentials. Well, similarly, if you have log base lowercase b of two numbers that are being divided by each other, you can actually split this up into two different logarithms that are being subtracted. The next property is really closely related to property number 3. What happens if I have a logarithm with base b of a value that's being raised to a power? So we'll say a to the n. Well, if you think about what that exponent means, that means I'm multiplying by a over and over and over again, which means I can theoretically use property number 3 to say, oh, well, this is just log base b of a plus log base b of a plus log base b of a over and over and over again, right? N amount of times. And so therefore, I can convert that into just multiplication. N times the log base b of a. So what that property tells me is if I have any exponentials in my logarithms, I can pull the exponent out and multiply by it. This property is really important because now I can go back to my first property and I can notice something. What happens if I do log base b of b to the x? Well, according to property number 5, I can pull that x out as multiplication and I get log base b of b, which of course we know from property 1 is just equal to 1. And so I get x. If I switch this around, it gives me x. So both of these terms, when I put them together, ended up giving me x. What does that tell me? That tells me that b to the x and log base b of x are inverse functions. So this is how logarithms are related to exponential functions. It's inverse function. This is the inverse function of exponentials. So this is important because now I can use logarithmic functions to undo exponential functions. When do we like to undo functions? Well, that's when we're solving equations. So now if I'm solving an exponential equation, I can use a logarithmic function to undo that equation. Well, if you look at your calculator, you'll notice, well, there's certain logarithmic functions that we use more than other ones, right? I can have log of any base. I can have log base 2, log base 5, log base 7, right? But there's 2 logarithms that we use a lot more often than normal, and that's log base 10 of x. The reason why we like log base 10 is for scientific notation where we're doing 10 to the power of 5, 10 to the power of 7, right? So log base 10 makes a lot of sense. So because we use that one so often, the notation for that, we just drop the 10. If you see log without a base, you can go ahead and assume it's log base 10. And then the other common one that we use is log base e. Right? In 3.1, when we first learned about exponential functions, we talked about the natural exponential function, where it was base e. And so logarithms with a base e are also widely used and are really, really useful. And we call this the natural logarithm. And we use n or ln to notate it. So if you see ln of x, that's log base e. Okay, I know this isn't the examples video, but I still want to go through a quick example just to kind of highlight those 2 things we've learned, just barely. So let's look at an exponential function where I have 1.1 raised to the x is equal to 5. Using my basic operations, there's no way I can solve this. I mean, I can guess and check, but that might take me forever to try and figure out, and that would only be an estimate of what x is. So how do I actually go about solving this? Well, there's a couple different ways I can look at this. First of all, I can do so by recognizing that logarithmic functions are inverses of exponential functions. So here I have an exponential function with base 1.1. I can use log base 1.1 to undo this exponential equation with base 1.1. But remember, when solving equations, whatever you do to one side, you have to do to the other side. So I would also have to take the logarithm base 1.1 of 5. That gives me log base 1.1 of 1.1 raised to the x power equal to log base 1.1 of 5. Log base 1.1 of 5 is something I can just plug into my calculator as long as I know how my log button works. But if I look at this left side, that looks a lot like this result right here, right? What happens if we have log of some base evaluating that same base raised to the x power? These things just cancel out and leave me with just x. And so my answer is just log base 1.1 of 5. And if you think about it, this makes sense. This follows directly the definition of a logarithm. Log base 1.1 of 5 is asking that question, what do I need to raise 1.1 to the power of in order to get 5? Which is exactly what this original question was asking. 1.1 to what power will give me 5? Okay, but that's not the only way I could go about it. Raise your hand if your calculator has a log base 1.1 button. I guarantee you it doesn't. which is why we have these commonly used logarithms. Your calculator will definitely have a natural log button. But how can I use that natural log when the base of this exponential function is 1.1? So let's start over here and think about this. Remember log property number 5. If I take the logarithm of something raised to a power, notice this base did not have to match this base for this property to work. But if I take the logarithm of something raised to a power, I can pull that power out. Which means even though the base of this is 1.1, I could still use the natural log to undo this exponential function. I could take the natural log of both sides. And let's see what happens. That leaves me with the natural log of 1.1 raised to the x power equals the natural log of 5. Natural log of 5 is going to be much easier for you to input in your calculator because you're going to have a natural log button. But then over here, what happens? You have log base e of 1.1 to the x. That exponent can be moved outside of the logarithm using multiplication. And from here, I can solve for x just using division. So my log properties, specifically property number 5, give me a lot of flexibility of which logarithms to use, which is why we have these two common logarithms that we use way more than any other ones, because logarithms are really flexible. Well, now let's talk derivatives. And similar to how we worked with in the last section with exponential functions, we're really just going to focus on base e. We're going to get to derivatives of different bases later, but because we can use the natural logarithm, log base e, in a lot of situations, we're just going to focus on the derivative of log base e. Well, to get this derivative, it requires a little bit of implicit differentiation. Let's go ahead and give it an output variable, y, and we're going to use the definition of the logarithm to rewrite this. Based off my definition of a logarithm, I can rewrite this as e to the y is equal to x, right? What exponent do I need to raise e to in order to get x? The reason why I did that is because I don't know how to take derivatives of logarithmic functions, but I do know how to take a derivative of an exponential function. So now, let's take the derivative of both sides. Notice we're still taking the derivative in terms of x, right? Based off of this, we're taking the derivative in terms of x, which means the right side is really easy. What's the derivative of just x? The derivative is just 1. But the left side requires implicit differentiation, what we learned about in 2.8. What's the derivative of e to the y? Well, what's the derivative of any e function? Derivative of e to the x is just going to stay the same. So the same is true for e to the y. The derivative is just e to the y. But because y is my output variable, I also have to multiply this by dy over dx, or y prime. Remember, you can use either notation. Remember that this represents the derivative, so now all I need to do is solve for that. I get dy over dx is equal to 1 over e to the y, just by dividing both sides by e to the y. Well, I don't want to keep this in terms of y. I want to get this back in terms of x. How? E to the y is just equal to x. So I get dy over dx is equal to 1 over x. Pretty cool. Kind of a complicated process, but you end up with this really simple derivative formula. So what's the derivative of a natural log function? You just get 1 over whatever the input is, 1 over x. Well, what's nice about us learning chapter 1 and chapter 2 first is we now have a lot of derivative rules that we can use for more complicated types of functions. Consider this. What's going to happen if you have a function inside of your logarithmic function? How would an inside function affect your derivative? Well, you can just use the chain rule. Why? Because I have a function inside of a function. So I can use the chain rule in this case. What does the chain rule tell me? The chain rule tells me that the derivative is going to equal the derivative of the outside function. My outside function is this natural log. And so what's my derivative? It's just 1 over x, or 1 over whatever the input is. So in our case, That's 1 over the inside function, f of x. But because I'm using the chain rule, what do I then have to do? I have to multiply it by the derivative of the inside function, which I can just notate as f prime of x. So if you have a function inside of your natural log function and you take the derivative, all you end up getting is the derivative over the derivative of the inside function over the inside function. I do want to give you one more thing to look out for, though, as you start working through some of your homework problems or working with logarithmic functions. I actually have another option here. What if f of x has a really, really complicated derivative, right? What if the derivative of f of x requires the product rule or requires the quotient rule because it's a function over a function or a function multiplied by another function inside of my natural log? Don't forget that logarithms have some really cool properties that allow me to work with two things that are being multiplied together inside of a logarithm, or two things that are being divided inside of a logarithm. So that's something I'll say with taking the derivative of the natural log of some function inside. Consider using some log properties first. See if any of the log properties will help you simplify your function before you take the derivative. That's it for our concept video, though. Go ahead and get started on the homework, and if you need some help on some problems, go watch the examples video. Thanks.